In this tutorial, we're going to do protein NMR. Protein is a big molecule, and what we're going to have to do is to pick a region of the protein that is a quantum region to do quantum mechanics on, and use the rest of the protein as classical, do a mixed molecular mechanics, quantum mechanics calculation. So let's get a protein, and we'll choose a PDB file, our old friend Cramden, for a small molecule. And now let's do NMR on a residue somewhere in the middle, say. So let's choose a residue, select a residue by, say, number, and we can just pick one here. Let's pick residue 14 for the heck of it. This is the residue down here, and this is going to be the quantum region. The rest of the protein, all these other atoms, will be included as a perturbation on the quantum region. That is, the point charges on these atoms will be thrown into the core Hamiltonian for this quantum region as an electrostatic effect. There's one other thing we have to do, however, that we need to cap off this quantum region with capping atoms to be the boundary between classical mechanics and quantum mechanics. And in order to do that, we want to cap this at sp3 single bonds. And we have a specific menu item here that assists in this. Extend to sp3 takes the existing selected region and expands it outwards until it can be capped at only sp3 single bonds. So that grew that selected region just slightly. So if we zoom in on this selected region, then this is it here. Let's display only this selection, and let's put some labels on here so we can sort of see what's going on. This is, again, residue 14, and we're going to, this is the quantum region, and so we have to tell the program that it is the quantum region. We have to name this selection as the quantum atoms. By doing so, we have a mixed quantum mechanical molecular mechanics computation. So these are the atoms that are the quantum atoms, residue 14 and a few atoms in the two neighboring residues. Now, the next thing, since we're going to do proton NMR here, we need to select the protons, and so these are the atoms that are going to have nuclear spins in which the chemical shift is computed and the coupling is computed. So let's take the amide proton, this one here, these two here, and these two here, all in residue 14. And we're going to name these as the NMR atoms. So basically, we're finished with the setup here, except for a couple things. Let's go get the NMR module and bring that in here. Here's the NMR module, and if we look at the setup of this, shielding and coupling, we'll see that the quantum atoms have been carried over from HyperCam and are set here correctly. The NMR atoms in the same way. There's 6 NMR atoms. What we haven't done yet is describe equivalent atoms. The equivalent atoms may or may not be desirable to set. This will make the shielding the same for each of those equivalent atoms. It will tell the program that they really are the same and to average the shielding for those atoms. So let's number these, or put labels on here so that we can see the numbers. We'll put a number label on this, so we have atoms 200, 201, 202, 203, and so on, and we're going to make 202 and 203 equivalent, and 204 and 205 equivalent. To do so, we go up and we just set up the equivalent atoms, and we've got 202 and 203 are an equivalent set, And we go to the second set and make 204 and 205 equivalent, and then we set the equivalent atoms. So that's the equivalent atoms. There are other things that we could set up in terms of the spectrometer frequency and so on and so forth. Let's leave it as it is at 300 megahertz. We can change that if we wanted to, but it's not pertinent to the discussion here particularly. So let's go and compute the NMR spectrum. We can, first of all, phase 1 is an electronic structure problem that calculates the shielding and the coupling. If we've done that, we can go on to phase 2, which is the NMR, Hamiltonian, and the NMR spectra based on the shielding and coupling. If we just click on this, we'll do both of those. This is a relatively small quantum region, so it doesn't take very long to do this. These are the coupling constants we've computed. There's basically numbers in the vicinity of 7, which is the amide proton, or the 204 and 205, which are the are also very much like an amide. These protons are connected to a nitrogen as well. These are the methylene protons, and this is the proton connected to the alpha carbon. The coupling constants are here. Some are positive, some are negative, and so on and so forth. And this is then the NMR spectrum. If we apply a line width, we can see that there are these protons here include the amide proton, which is this one, and then there are these others too. This is the amide proton is deshielded because it's connected to the has a large chemical shift because it's connected to an electronegative nitrogen. Anyway, this is the NMR spectrum for that particular residue. We can zoom in on this a little bit if you like, and so on, and then see the individual peaks here if we wanted to, but basically that's the spectrum of that particular residue. It is not the exact way to do it. The exact way would be do the whole molecule all at once. In this case, we're choosing some specific protons and specific residue to compute and use the rest of the molecule as sort of a perturbation on this residue. Anyway, that's the NMR spectrum of a protein.